Good morning, everyone. Uh, Before we begin, a very happy new year to all of you, and thanks for coming. So early in the year, this is the first of the AFMS seminar series for 2023, and it's also the first HDR research seminar series that has been organized by the Faculty of Engineering. So I would like to acknowledge both the Faculty of Engineering as well as the Australian Fluid Mechanics Society for supporting this research seminar series. I would like to begin with the introduction of our guest speaker, Dr. Ricardo Vinuesa, who is an associate professor at the Department of Engineering Mechanics at KTH Royal Institute of Technology in Stockholm. He's also vice director of the KTH Digitalization Platform, lead faculty at KTH Climate Action Center. Dr. Ricardo studied mechanical engineering at the Polytechnic University of Valencia in Spain. And he received his PhD in mechanical and aerospace engineering from the Illinois Institute of Technology in Chicago. His research combines numerical simulations and data-driven methods to understand and model complex wall-bounded turbulent flows, such as boundary layers developing around wings and urban environments. So I'll hand it over to Dr. Ricardo now.
Okay, thank you very much for the kind introduction, and it's a great pleasure to be here in Australia, escaping from the Swedish winter. It's now nice summer here. Thank you, Julio, for the invitation. I'm going to give an introduction to artificial intelligence, very general introduction, and I'm going to talk about some possible applications to computational but also experimental fluid dynamics. So this seminar today will complement the seminar that I will give next week, which will be a bit more on more recent or cutting-edge methods. Today will be more about basic approaches and techniques. So hopefully both seminars will be complementary. And I would also like to acknowledge the European Research Center, the Research Council, the ERC, and the Swedish Research Council for funding of this research. So a little bit of a general introduction. Many of the problems in science that we are experiencing nowadays are not amenable with traditional computational, theoretical, or experimental techniques. We have now the ability to generate more data than ever. No? I mean, according to IBM, over 90% of the data ever created was generated in the past 2 years, and that keeps happening every 2 years. So there is certainly a huge increase in the capabilities of producing data, and that has produced such large volume of data and the need to be able to tackle all this information that has in a way led to the creation of a new discipline or a mix of disciplines, which is data science. No? I mean, we need to be able to develop scientific approaches to tackle this data and to be able to do something useful with it. So data-driven discovery has been postulated as another pillar of science, no? That could in a way complement experiments, theory, and simulations. And this is something, for example, by Hay and others who try to state these possibilities of using data-driven methods in a complementary way with the other approaches that we know for science. So that's a little bit what we are trying to describe with data science, with data-driven methods. It's a mixture of disciplines. There's a bit of mathematics, statistics, computer science, information science, and many other things. No? So we really need to, and it's in a way quite multidisciplinary, because you don't only need the physical or technical knowledge on the data, you also need the computer science aspect, the architectures, and all these machines that we need to use to be able to tackle the data. So in a way, there is quite some challenges in being able to manage these very large databases. That's where you need experts from many different disciplines. And the definition of data science or data analysis proposed by John Takei in 1962 in a way combines machine learning. Machine learning has to do with prediction and developing faster and scalable algorithms. So this is more on the computer science side, but it's also an aspect of statistical learning, which has to do more with interpretable models. No? So being able to obtain from your data something that is not a black box, that we can try to understand something from it. And I will be also emphasizing a bit more this interpretability of the black box as we go with the presentation. So this is a little bit what we mean with data science. I'm going to give you one possible classification of data-driven methods, and this is, well, my personal view on how to classify the methods. If you ask around or if you read the literature, there is not one unique classification of methods. This is basically a zoo of well, approaches. So this is one possible way to put some order, no, in all these possible ways to tackle all these large databases. So it's difficult to draw borders among the methods, but we're going to try to use a common language for today's presentation. And artificial intelligence would be perhaps the broadest term that encompasses many different applications to robotics, computer vision, voice recognition, NLP, natural language processing. This is very trendy nowadays with this ChatGPT, you know, the big language models of Google and other large companies, which actually has a lot of promise. These are in the end transformer architectures. And artificial intelligence is a quite general concept, which, I mean, if we try to provide a definition or a formal definition, AI was basically initiated by McCarthy and others in 1955 as a discipline of computer science that was focused on developing machines that can imitate intelligent behavior. Right? It's kind of a bit of a broad definition. And I have to say that McCarthy and others, well, McCarthy, they were very optimistic, no? Because they had funding for a summer project, and their idea was to solve AI in that summer program. In a couple of months, to AI is done, and this is quite some decades ago. No? So we are still trying to figure it out. But at least they have some, well, some optimism. That's the first step to do something, and they have some interesting definitions, no, what AI actually is or what is not. And of course, there is some subsets of AI. There is weak AI and strong AI. The weak AI is related with systems that perform very well in very narrow tasks. And strong AI is a bit of a theoretical concept of developing an artificial intelligence that can perform very well, as well, or even better than humans in many tasks. So basically this concept of artificial general intelligence for which there are no examples yet. So this is a little bit science fiction at the moment, but there is, Google has some ideas and there is a little bit of progress in this direction. If we want to differentiate AI with other data-driven methods that I'm going to talk about in the next slides, is that AI does not necessarily rely only on data. That's maybe one definition or one difference that one can establish. So for example, AI can also include the behavioral models. So if you're using an algorithm to analyze Facebook data and see which is your favorite football team to give you advertisements of t-shirts or whatever, and they're using, in addition to your data, some psychological behavioral models that goes a little bit beyond just purely the data, then that could be considered as AI. And this is one, again, this is not the only classification of methods, but this is the way that I look at these various approaches. So AI is data plus something else in general. Whereas if you go into something a bit narrower, then you can consider machine learning or data-driven methods. And in this classification, I consider both as synonyms. Some people make differences between both. I would consider both as synonyms. And machine learning was defined by Samuel, also in the late 50s, as a subfield of AI, which is focused on the creation of machines that have the capability of learning without being explicitly programmed to do something. So one can solve a certain task without being explicitly programmed to solve that particular task. I like maybe a bit of a more updated definition, or a definition that applies more to what we do in mechanical engineering, fluid mechanics, and it's basically being able to build models from data using optimization. That's what I would call machine learning, and to me that would be equivalent to data-driven methods. So we are using data, using optimization to build models. And of course, there are many examples of machine learning methods. Here's where we want to classify things a little bit. There's decision trees, regression, clustering, classification, and deep learning, or neural networks. which is a subset within machine learning. So AI is the broader term. When you're using data plus something else, when you're using only data, then it's machine learning or data-driven methods. And then deep learning is one particular example of machine learning method, but there are many others, as we can see in this slide. So we are now getting to narrower concepts, and that's where we get into deep learning. So deep learning is one particular area within machine learning that has to do with using neural networks. And I will talk more about neural networks a bit later in the seminar. One particularity of deep neural networks, and deep learning has to do with deep neural networks, is that you have more than one hidden layer between the input and the output. So this will become clearer when we look at the structure of a neural network. But basically, if you have more than one hidden layer in between, that's a deep neural network. If you only have one, then it's a shallow neural network. And then that would not be part of deep learning. Interesting things with neural networks, they learn in a hierarchical way. So all the different layers have to do with a concatenated application of operations, of nonlinear operations, which means that deeper neural networks will allow us to learn more complex relationships in the data. And also they go from more abstract concepts in the first layers to more and more concrete and complex concepts at the end. So if you want to identify vehicles in images, perhaps the first layers are going to be finding a mirror or a wheel, and then through the concatenated application of all these operations, as you go deeper in the network, you're going to build the mirror and the wheel to something that looks like a car or a train or an airplane. So the first layers look at things that are more abstract. The last layers are able to hierarchically build more complex features. That's a little bit how neural networks work. And of course, they require massive amounts of data, depending on the application. Massive is always with quotation marks because everything is relative, depending on the complexity of your problem and the capacity of prediction of your architecture. Massive will be order of thousands or order of hundreds of thousands, but that has to do with the concept of big data, which is the discipline that has to do with the accumulation, but not only accumulation, also curation and management of large databases to train these neural networks and other machine learning techniques. But of course, neural networks are the most data hungry. So big data has to do a lot with neural networks. So that's a little bit kind of like a general introduction of what machine learning or AI, which is a bit broader, means generally. And now I'm going to be describing a little bit how we can use it in our problems that are important for us in fluid mechanics, in turbulence, and in some other related applications and how we can actually learn something from them. So this video, which I hope works. It's a bit of cliffhanger. Is it going to work or not? It works. So this is now a relatively old simulation. We did it now almost 8 years ago. This is a DNS, a numerical simulation of the turbulent flow around a wind section. And this is a NACA 4412 5-degree angle of attack, Reynolds number 400,000, which at the time it was actually quite high. Now we can do something even higher, but you can see really I'm showing you this video to give you an idea of the wealth of data that we have. This is a quite complex flow case with turbulence, pressure gradients, not mean separation, but incipient separation, vortex in the wake. So we have a lot of data. This is many terabytes of data that are composing this database. And all this wealth of data is something that we can hopefully exploit with our machine learning techniques. I mean, we can really see all these individual coherent structures, all these individual vortices, how they're interacting, how they're merging and splitting, how they're advancing in time. All this information, we should hopefully be able to exploit it with data-driven methods, not to understand turbulence, to try to control turbulence. I will be talking about these things in the seminar next week, which is a little bit more on the research side. But this is just to illustrate a bit that certainly our field in fluid mechanics is one that, well, it's actually quite attractive for machine learning because of the availability of data and the numerous open questions that we have. Okay, so This is a little bit of general motivation of why machine learning actually helps in other areas. No, I mean, if we just look at the 17 Sustainable Development Goals of the United Nations, we actually did a systematic assessment of how artificial intelligence can help to achieve, or it can help to hinder the achievement of each of the 17 goals. But we went into the detail of 169 targets. No, the targets are sub-goals within these big sustainability areas of the United Nations. Let's remember that this is the 2030 Sustainability Agenda of the UN. This is a study that we published in Nature Communications now 3 years ago. And we found that 79% of the targets of the UN can be positively affected by AI, whereas 35% of the targets can be inhibited by the development of AI. No? And this has to do with many of the things that I'll be talking about today and next week, how we can develop better technical solutions that can help us on the positive, but at the same time, we may be able to achieve some targets and hinder others, no? By having more efficient solutions to obtain a certain resource, we might be destroying other resources, or we might be increasing pollution or increasing inequalities. No? So these are perhaps technical and societal aspects that one needs to keep in mind with the development of AI. But in principle, the potential is quite positive. I mean, we should be using this, no? Because the research tells us that there is quite some positive potential of AI to be able to do something good. Okay. And talking a little bit more about neural networks and the black box and all these things, what I'm showing you here is the possibility of using neural networks in a way that they are not black boxes. No? Many machine learning models are interpretable, and interpretability is defined in the sense that you can make an easy connection between the input and the output. So you can write an equation, or you can find a decision tree of how input and output are connected. But neural networks that I've been talking about, they are not interpretable. They are black boxes. So the input and the output cannot be easily connected. And that's a problem, no? Because if you're using neural networks to make predictions for reducing the drag of an airplane, but even more, if you're using neural networks to decide the medical treatment or to decide if someone is going to get a loan or not, and this neural network is not interpretable, then that's a problem, no? Because obviously you're going to hinder the achievement of those sustainability goals if you're not having interpretable models. So in that sense, we actually gave the example. We have an article in Nature Machine Intelligence where we gave the article, the example of being able to use satellite data to predict regions of poverty and help achieve some of these UN goals, and how one can use symbolic regression to end up with an equation that reproduces the accuracy of the neural network while having that interpretable capability. No? So you can hopefully at the end reproduce the accuracy of the neural network with an equation. No? And this is not something straightforward. I mean, Kramer and others, they have a very nice article also where they look at these methods, and there are different ways of doing this with genetic programming, but there are all other symbolic regression tools to do that. At the end of the day, what you want to do is try to preserve the accuracy of the model that you get from a neural network, but be able to open the black box and get an equation, no, that connects inputs and outputs. So this is a very, very promising area, but also a quite challenging one. And that's interpretability. And this is a little slide that I have in my machine learning course at KTH. So basically, and this is borrowed from some colleagues in the US, no? Changing random stuff until your program works is hacky and bad coding practice, but if you do it fast enough, it's machine learning and it pays 4 times your current salary. It's a bit, it's not that bad, but it could get that bad, no? It's a bit of a warning that I give my students at KTH. My main take on this is simpler models are preferred, no? So we have, to do many of the things that I'll be discussing today and next week, we have many tools, many traditional tools based on linear algebra, based on fundamentals, on very, very established techniques. We should do those first. One should not just say, okay, I have a new problem, I'll take TensorFlow, I'll throw everything in a neural network and see what happens. I mean, you should not be doing that, right? You should try to understand the classical methods, see what is the performance that you expect, see which cases you expect to get good performance and which ones not and why. And then in that case is where you can actually go to neural networks and many other things. There's many machine learning techniques that one can use, but one should go through the simpler things first, no? Because they're usually more interpretable. That's a little bit what we also want. Okay. So this is a bit of an intro to machine learning, and I'm going to talk about two things today. One is to make predictions with basic neural networks, with sequences, temporal sequences, and how we can understand the techniques for sequences. And then I'm going to talk about physics-informed neural networks, PINs, which can be helpful for some simulations, but also for some experiments. No? And since here in this department, there's a lot of numerical and experimental work, I think that PINs can be a tool that can be helpful in some applications. But I also want to give some notes of caution on the usage of PINs as well. So let's start with the predictions of sequences and what architectures to use. This is also a bit of an intro to how one can define learning. No? I mean, in supervised learning, we have labels. So we're telling a network, okay, this input is corrected with this output and this input with this output, and the network learns from those labeled data sets. This is very typical in predictions or supervised classification. So many of the things that I'll be talking about today is based on this, on supervised learning. But there are other cases where we want to do unsupervised learning. And in that case, the data is not labeled. So we are not telling the network, this input gives me this output. The network or the machine learning model decides that. No? And an easy example for this is clustering, but also, for example, doing POD. I mean, POD is a very simple example of unsupervised learning because the modes that you get come from the algorithm. You're not telling the algorithm, this flow has these modes. No, it's the algorithm itself that comes up with it. And then there is another, a third type of learning, which is reinforcement learning. And that's very promising. I'll be talking a lot about it next week as well. We have quite some research on this area. And in reinforcement learning, you don't tell the network, you only tell the network a particular goal, a reward. So I want to minimize the drag of this device. And then the machine learning model interacts with the system, tries stuff, a bunch of stuff, and then it makes errors, of course, and then it picks the trajectory that gives us the optimal performance in terms of that reward that you have defined. So reinforcement learning is also unsupervised, but it works a bit differently. That's why it's classified as a different way of learning. And I see that there's a lot of potential also from reinforcement learning to do many things, although it's quite tricky to get it to work well, in general, let's say, but there is a lot of nice potential with reinforcement learning. So today we will focus mostly on supervised learning. We're going to define sequences, temporal sequences, and to do that, we're going to use a simple model of the near-world region of turbulence. This is the 9-equation model by Moelis and others, where the spatiotemporal data is obtained from 9 spatial modes, 9 fixed modes. So we will just get the temporal coefficients. This can be run very easily, and all this data is available online, so I can share everything. We generate 10,000 data sets of 4,000 time units each. So we generate a lot of data that can be very easily run in Python, in MATLAB, whatever you want. This just takes a few minutes to train neural networks and see if we can reproduce the dynamics of this. But by the way, this that we are showing for a model of the near world region of turbulence, we published last year a paper where we did the same on a minimal channel for a real turbulent flow. So not a model of the near world region, but a real turbulent flow, a minimal channel in this case. So what I'm going to show today for this toy problem, if you wish, also works for turbulence. Okay. So this is what the 9-equation model gives us. These are the temporal coefficients of the 9 modes, and this is the front view, so you can see the stringwise vortices and the high and low speed streaks. You can see the spanwise movement of the streaks. So this looks a lot like the near world region of turbulence. No? This is a good model to start to play with. And this is published in Physical Review Fluids. So Prem Srinivasan was the main author for this. And again, all the data and the codes are available online. Okay, so this helps me to introduce the most basic type of neural network, which is the so-called multi-layered perceptron NLP, and it looks like this. In this very simple architecture, what you have is on the left the inputs. So you have an input vector, all the quantities that you want to predict, that you want to define as input are on the left. On the right, you have the output vector. And in between, you have the hidden layers. Here we have two hidden layers, which makes this a deep neural network. If we only had one, then it would be a shallow neural network. What you realize, which is actually quite interesting, let me go to the next slide, is that we are going to use these 9 temporal coefficients, right? These 9 sequences, and we want to use the 9 values at the current step to predict the 9 values at the next one. And the next one, and the next one, and so on. So the output is always having a size of 9 because there are 9 coefficients that I want to predict, but the input can be larger because I may consider several steps to make the prediction in my input. So the size of the input layer will be 9 times p. So p is the number of steps. If I consider 2 steps, then I have 18 values in the input. In the output, I will always have 9. And then in between, I can have any number of neurons, and this is something to basically optimize. It's a hyperparameter to optimize when I'm training my neural network. How does a multi-layered perceptron work? Essentially, what we do is that we're going to train parameters in each of these layers, which are a weight matrix and a bias vector. So what a neural network, a fully connected neural network like this one does, is a matrix vector multiplication, and then at the end, a nonlinear activation. Okay, that's basically the key. So if we zoom in into one neuron, what we get is this operation. I have the weight, the weights of the matrix of weights multiplied by the vector on the previous layer. I add another vector, which is the bias, and this G is a nonlinear function. So if I did not have this nonlinear function, all these intermediate layers would be completely useless because I could reduce everything with one single operation, right? Because all the linear operations could be combined into one. But because I have a nonlinear activation here, this is what gives us the capability of, in principle, predicting any smooth function, in principle, given enough parameters of my network. This is what makes having a deeper neural network more powerful in terms of prediction because of the non-trivial concatenation of nonlinear operations as we are going deeper into a network. So essentially, to train a neural network is to use backpropagation to find these two sets of parameters. Again, the weights, the matrix with all the weights and the biases. So these are just fitting coefficients, if you want to put it a bit simply. And this G is the activation function. This can be, there are different activation functions that you can use depending on your problem and depending on the data that you're having. This is a sigmoid, but you can have a hyperbolic tangent, you can have a rectified linear unit. There are many different types of activation functions. The point is that they should be non-linear, because if this activation is linear, then you just have a matrix vector multiplication, which is a trivial operation. So the strength in prediction of neural networks comes from this non-linear activation. Okay, that's the key. And then the training process is basically as follows. You divide your data into a training and validation. So you're going to use part of your data for the neural network to adjust the weights, and you're going to save some of your data, typically around 20%, for validation. The validation data is not seen by the network when adjusting those parameters, because we want to see if our network can generalize, if our model can work in cases that have not been seen during the training process. And the idea, a typical training would look like what you see on the left. So I'm showing you the loss as a function of the number of epochs. An epoch is just a pass through all the training data. So I'm adjusting the parameters through all the training data. Once I'm done with all the training data, I do it again. This is done stochastically, so there is a little bit of variation of the points that I'm using. And typically, your loss will get smaller as I increase the number of passes through my training data, because I'm fitting the data better. And the loss in the validation data, which has not been seen during training, that's typically higher, but typically it also goes down. So this is a normal training. On the right, what I'm having is something called overfitting. So what happens when I'm having overfitting? My training loss is going down, so I'm fitting my data that I have seen during training better. But when I'm trying to generalize, at some point my error increases. So my network fits very well the data that it has seen, but it's not able to extend to data that it has not seen during training. And the overfitting typically means that I don't have enough data to generalize. So I have a very big network with many parameters, and I'm just overfitting the data that I have. So I need to either make the network smaller, or even better, have more training data, more examples during the training, so my network can learn to generalize beyond those training examples. Another possible problem during training is the underfitting, and that's if this curve is very high. That means that my network is probably small enough, it's too small to fit the data. So I don't have enough coefficients, I don't have enough parameters to fit my data, and the loss is very high. Even if it goes down with training, it remains very high. Okay, so playing with the possible problems of overfitting and underfitting, I can try to define the parameters of my network. Okay. What happens with the NLP, with the fully connected network? It's a network that provides me point predictions. This is important. So if I'm having a temporal sequence, if I have 9 coefficients and several previous steps in time, the network doesn't know how the data is organized in time, because everything is provided as a long list in my input. But of course, the data has temporal information. It has temporal correlations there that are not being exploited by the network to make the predictions. So the NLP is a simple architecture that doesn't necessarily perform very well, but it's a good baseline for the type of performance. In fact, here we needed 500 steps. So that's a total of 4,500 values in the input, because I have 9 coefficients, to obtain reasonable predictions. So that's a huge input of my network, because my network doesn't understand how the data is organized in time. And you can see that the flow field looks reasonably okay, but I mean, it's not perfect in terms of the span-wise movement of the streaks. And if we look at the performance, this is the mean flow, this is the string-wise velocity fluctuations, this is the Reynolds shear stress. I'm having 10% error in the mean, 36% error in U square, no, in the string-wise velocity fluctuations. So clearly there is room for improvement, because my network doesn't understand those temporal dependencies. If we play a little bit with the architecture, so changing the number of layers, of hidden layers, and the number of neurons per hidden layer, I can get a bit better. So I can go down to 18% error in the fluctuations, but still there is so much that you can do by changing the architecture. No, there is something else that one should probably try. And this is going to another architecture that allows me to exploit the temporal information in the data. This is what we call a recurrent neural network, which basically exploits the sequential nature of the data. And this is what it looks like. I'm showing you at the bottom the input. So this is the 9 coefficients at the current step. This is at the one before, and so on. And this is the prediction of the 9 coefficients at the next step. No? So this is data enters from down here. Data predicted data is going to come up from the top. And the key of the recurrent connection is basically this, is the fact that the output of one step is connected with the input of the next step. So now the data is not just, disorganized, put as a long list with steps from now, or 10 steps ago, or 100 steps ago. Now I know through these recurrent connections how things are organized in time. And that allows me to understand those temporal dependencies of the data, basically. If we zoom in, and this is a bit technical, this is a particular implementation of recurrent neural network called the long short-term memory network, the LSTM. This is actually, this is the autocomplete in your phone is based on this type of architecture. So if your autocomplete is autocompleting things that it shouldn't, it's your fault because you train it wrong. So that's basically depending on what you train your network with. Essentially, it uses a gating mechanism that you can see here. So this gating mechanism is trying to understand how important is the past information, the very old information. So the network is realizing that the recent data is probably quite important to make the prediction of the next step, obviously, but the data from 5 steps ago, 10 steps ago, 100 steps ago, how important that is, right? How is that weighting function designed? This is what these gates are actually taken care of. So you forget some of the older data, and in a way you try to incorporate those temporal dependencies in your predictions. So this is what the LSTM architecture is actually doing. And what we see is, I mean, here I'm doing a parametric study of the number of steps that I have in my input. Remember that before I needed 500 steps. Now I can get away with 10. So clearly I need much less data because the network understands how the data is organized in time. And I have one hidden layer or two. So I'm changing that. If you compare with I'm going to compare later with the results of the MLP, but you can see that the errors are already much lower. And this is 2% error in the extreme-wise velocity fluctuations. So the agreement is actually pretty good. And you can see that the predictions are basically on top. No, this is the mean, the extreme-wise fluctuations, the Reynolds shear stress, even the data, the flow field looks much more realistic. And I have 2.5% error in the U square. Comparing with the MLP, so we had for 10,000, so actually when we train with 1,000 data sets, we have 3% error in U square and 18% error in the MLP. If we keep training with more, so increasing the number of data sets, we go down to 2%. There is even much more improvement by increasing to a second hidden layer. So if I compare this case with 100 data sets with case number 1, I reduced the error from 14 to 6%. So making the network deeper improves the data. And if we do a much longer training, we're going to reduce significantly more the error that we have here. So there is quite some hyperparameter tuning that can be done in terms of the number of hidden layers, the number of neurons, the number of data sets. But the point is that we're converging towards lower error, basically. But this is all statistical so far. Okay, what if I'm interested in instantaneous predictions? No, I mean, how much error do I make in the next step? Well, actually, this is just to show you that even the higher order statistics are in very good agreement. The vorticity fluctuations, skewness, and flatness, everything is quite good. But for the instantaneous predictions, you can see the blue is the reference and the red is the LSTM. We have 13% error. So it's actually not on top. The statistics is very good, but the instantaneous predictions are not so good. And this is because this is a chaotic system. So we can think that even if I make a very small error in the prediction of my next step, this is a small perturbation that is going to take me in a different trajectory. So in principle, you know, the loss function, which you can see here, this on the order of 10 to the minus 9. So I'm having an error in the prediction of the coefficients of the order of 10 to the minus 9. It's a minute error, but that's still enough to create a perturbation that takes me to another trajectory. So my goal here is not to get 0% error in the instantaneous predictions. My goal is to understand if I learn the proper dynamics, the correct dynamics of my system. That's what I want to assess. And to do that, I can look first at the Poincaré map, for example. So I look at the correlation between the first and third coefficients. And you can see that red is the LSTM, blue is the reference, they're on top. So even if the instantaneous values are different because I'm in a different trajectory, the correlation between those two coefficients is actually correct. And so the interaction between, in this case, the first coefficient is the laminar base profile, and the third coefficient is the stringwise vortices. So in this case, these two coefficients are in very good agreement. And another thing that we did was to perturb the original system. So not the predicted one, but the original one, and then analyze how that perturbation takes me to a different trajectory. And if you do that in an exponential plot, this straight line is actually what in the log plot, in logarithmic plot, what you see is a Lyapunov exponent. So this gives me an idea of how quickly I'm deviating with respect to the original trajectory. And what we see is that perturbing the original system with an error level similar to that of the neural network, the deviation in the original system with respect to the original trajectory is basically the same as the error that I make with my neural network. So what we can conclude with this Poincaré map and the Lyapunov exponent is that I learned the dynamics of the original system up to an error of 10 to the minus 6. This 10 to the minus 9 was the loss function, which is normalized a bit differently. If you transform that into the norm of the errors, of the deviation of the errors, that's around 10 to the minus 6. So with a very small error in the coefficients, well, I'm going to learn the dynamics of my system very well, but up to this level of accuracy. And precisely since I get good agreement in the Lyapunov exponent, I get a good indication that I learn the dynamics up to that level of error, basically. Okay, so this is about what we can see with the LSTM. This is the first part of the presentation. I want to basically summarize a couple of things. The MLP, the fully connected network, is the most basic architecture. It's very simple, but you can just get an idea of the baseline performance that you can get. If you have temporal dependencies, if you have data with time, the LSTM, the long short-term memory network, is probably going to give you something reasonable. It's not always super easy to train, but it usually gives you something reasonable. So if you have temporal information in the data, you need to exploit that temporal information in the data. The MLP is not going to exploit it. So your predictions will be much better if you're using a network that can learn the temporal information. The LSTM, I mean, this is quite old. I mean, there's more updated architectures nowadays. So something that we are doing now to produce inflow generation. So we have just published in JFM now an article where we use a transformer. So basically an attention-based network to predict the temporal dynamics of the inflow generator for our turbulent boundary layer. Transformers are more powerful than LSTMs, and they're very trendy nowadays. They're very large models and NLP, natural language processing. The point of transformers, or the advantage with respect to the LSTM, is that the LSTM can learn the sequential nature of the data, but it assumes that the data is basically organized in a certain way, and the importance of the old data decays. No? That gating mechanism basically says that the old data is less important and the recent data is more important, and how that importance is changing, that's defined by the gates of the LSTM. But the transformers, which are originated in analysis of text, natural language processing, they don't have that restriction. Because if you think of a sentence, you are looking at the words in a sentence, it doesn't mean necessarily that the word next to another one is the most important to predict the next word. It could be that the subject, which is at the beginning of the sentence, is the most important word to predict the next one. Right? So you don't need the data to be completely organized one after the other. And transformers, because of the attention mechanisms, are very good at establishing those connections between, you can call it words, you can call it velocity fluctuations, that are not next to each other. So that's why transformers work even better than LSTMs in turbulence, because of course you have small scales for which the recent information is more important, but the flow history and the impact of the larger scales, that comes from probably several flow through times or flow over times upstream. No? So you need to have this multi-scale character of the temporal impact of the scales to make the next prediction. And that's something that the transformer can do because of that softer assumption of the sequentiality of the data, basically. So if you're interested, I can share the paper later and we can discuss that. But transformers, I really think, are the, well, maybe not the only feature, but one of the big features of temporal predictions in engineering data, but in turbulence and fluid mechanics in particular. Okay. Although the LSTM is a very good start. So since today is about introduction, then we can talk about the LSTM. Now, the second part of the presentation has to do with PINs, physics informed neural networks. And I think there is some potential of this technique. This is, of course, this was introduced by Josh Karnadakis group in Brown University. It's a very interesting idea in which what you do is that you formulate the governing equations, typically PDEs, and you exploit the automatic differentiation of neural networks to build the governing equation and solve these governing equations with the machinery of training neural networks. Okay, I'll get to the details in a minute. In the meantime, I just want to show one example. We published this in Physics of Fluids in 2022, and we looked at the 2D runs equations for incompressible flow. Okay, so we just take steady runs equations, and we want to solve the runs equations without, a model for the Reynolds stresses. So we'll just solve all the variables here using the framework of PINs. Okay. So let's see a little bit about pros and cons of PINs with respect to runs, solvers, and other approaches. Basically, the framework looks like this. I have my domain. This is a periodic hill. I'll show it later. The red dots are boundary conditions. So I need boundary conditions for all the quantities, including the Reynolds stresses. That's the downside of pins, because I need to know the Reynolds stresses. This could be interesting in experiments, because in experiments, maybe you have a lower resolution and you have the Reynolds stresses, but you can zoom in the domain and resolve with high accuracy all the quantities in the domain. These black dots are the collocation points. And the idea, the automatic differentiation, has to do with the backpropagation that I was mentioning before. When you train a neural network, you're calculating the partial derivative of the loss function with respect to the weights of the network. And that's implemented to calculate those derivatives analytically. They're exact because you have a function that you can differentiate exactly. So the derivatives are calculated with, well, they don't have any error in principle, those partial derivatives, which means that I can get away with relatively coarse meshes. I don't need to really resolve the gradients as much as in a RANS simulation. So I can get away with a resolution that is much coarser than that of a RANS solver. That's the advantage. The disadvantage is that you get RANS equations, you do a finite volume formulation, and then you discretize and you integrate in time, or you solve it for the steady equations. That's going to be much more efficient computationally than to do it with pins. Pins are probably at least 10 times slower than a commercial RANS solver for the same mesh. But since you can get away with a much coarser mesh, then the cost is very similar. So we have tried our pin simulations with OpenFOAM, and the computational cost is very similar, with the advantage that in a RANS model, you need to have, well, basically the model for the Reynolds stresses. So that gives you an error. With pins, no. With pins, you have very high accuracy also in the Reynolds stresses. I'll show you some of the results in a minute. But the point, the main takeaway message here is that we are solving from the RANS equations the mean flow, the pressure, and the Reynolds stresses. So that's everything that we solve at a cost similar to that of a RANS simulation because the mesh is coarser. That's the main idea for now. And you can see the implementation in terms of flow is actually very easy. It's actually very straightforward. And I can also share the code afterwards. Everything is available online, so you can look at it. It's a few lines because, to calculate the derivative in X, you get the tape gradient X. The second derivative, you take the tape gradient of the first derivative. This is very, very straightforward. This is a few lines in terms of flow. So this is not difficult to implement. But of course, there is a little bit of hyperparameter tuning with a number of hidden layers and a number of neurons and so on. But the implementation is something that is quite straightforward because, again, we are just using the machinery that already exists to train a neural network. So all the elements are in place, basically. Okay. So let's look at some examples. The first example that we took was just to make sure that pins was giving us something reasonable, was the Farner scan boundary layer, so the laminar pressure gradient boundary layer. So this is, of course, something trivial. No, this is something that we can solve very quickly with any method that we want. But this is as a sanity check. We actually obtain perfect agreement with respect to the theoretical solution for the Farner scan boundary layer. So in principle, that means that pins for this trivial case gives us something reasonable. Now we can go for something a little bit more interesting. This is a zero pressure gradient turbulent boundary layer up to Ari theta 7000. And this is high resolution. This is basically DNS data, a little bit coarser than DNS. So you can see the turbulent boundary layer, and what we do is that we compare the UV and the Reynolds shear stress between the prediction and the reference. We get 1% error in the mean. And what is interesting now, the Reynolds shear stress, we get 6% error. So this starts to be much better than what you can get with a commercial solver, no? Because again, it depends on which model you're using. If you take SST, which will work reasonably well for a zero pressure gradient boundary layer, you're assuming something about the Reynolds stresses that will not give you this level of accuracy, no? And you can see the comparison of UV. I mean, the results are actually pretty good. So we can obtain very good agreement of the Reynolds stresses in the context of the ZPG turbulent boundary layer. But if we go to more complicated cases, for example, pressure gradient boundary layers. This is the work by Alexandra Bobke and others from some years ago. These are cases with constant beta, with constant pressure gradient parameters. So these are near equilibrium boundary layers up to theta 3000. And again, what we can see, well, the integral quantities, the skin friction coefficient, the shape factor, the mean 0.28% error, and even in the Reynolds shear stress, 8% error. So as you can see here, when you have this pressure gradient is not so strong, it's a constant beta of 1, but still you have a quite pronounced effect in the UV, and this is captured by pins, by the physics-informed neural networks. So we can again obtain very good predictions of the Reynolds stresses, even in this more complicated case. Perhaps more interesting is our turbulent wings. So this is Vinuesa and others, 2018. By the way, this database, we have data up to Reynolds number of 1 million. And this is essentially DNS resolution. So all this data is also available. We took the 200,000 Reynolds number case. We took this domain that you can see here, and we tried to compare the predictions from runs and the predictions from bits. And well, the mean is actually again in very good agreement, 1.5% error. The Reynolds stresses, well, 9% error in the U square. We get a little bit more in the Reynolds shear stress, but you can see that we first of all capture quite well the anisotropy of the Reynolds stresses, which depending on which runs model you use, you will not get that. But also we get the outer peak. Of course, we don't get an excellent prediction of the outer peak, but we find the energization of the outer layer structures from the APG. This is a non-equilibrium APG, obviously. So this is a more challenging case. And again, we get something reasonable from pins. And keeping in mind that computationally, I mean, this is similar to a runs, no? I mean, this still you need to think of these results in terms of what you could get with a run simulation, in terms of the accuracy that you can expect. And if we look at periodic hill, where you have actually separation, so this is the prediction and this is the reference, and once again we can find well, the separation and reattachment points in very good agreement. The mean profiles are on top of each other, so you can see here in different regions of the periodic hill how we can get a pretty good prediction. Less than 3% error in the mean, and on the order of 20-28% error of the Reynolds stresses. This is a more challenging case because you have separation and you have many other things happening at the same time. But we get something that is quite reasonable and quite acceptable from the perspective of pins. Okay, so this was about using pins in the context of the runs equations, but I wanted to also bring a couple of examples from experimental fluid mechanics, because we have a couple of papers on using pins for experimental fluid mechanics, which was probably the original intention of the pins group, no? To be able to sample from data. Their paper in Science was about taking basically data from measurements, no? Taking data from measurements, from very sparse measurements, and reconstructing the flow field from those sparse measurements. No? That's a little bit what we can also do with some of our work. So this one on the left is about improving the measurements. This is a zero pressure gradient turbulent boundary layer just published in Measurement Science and Technology. This is just came out. I got the email yesterday, so this is really available now, open access. The idea is that so these are PIV measurements of a zero pressure gradient turbulent boundary layer, where is the U, the V, and the Reynolds stresses. The U is okay. You're comparing with high resolution LES, basically DNS. The Reynolds stresses, they're okay, not perfect, but they're okay. And the V, the one normal velocity, is it's very noisy. No? It's a very small quantity. It's 3 orders of magnitude smaller than the mean. The V is really bad. With pins, we can correct a little bit the Reynolds stresses, so we get a bit better agreement with the reference and the Reynolds stresses. But the key is that we can correct the V. So we get the right one normal velocity. This for a set PG case, but we have also done it for pressure gradient boundary layers and also for boundary layers with flow control, with blow transaction, where of course getting the V correct becomes more important, no? Because then you really want to see how the momentum injected in the boundary layer is really propagated in the one normal direction. So for improving measurements, pins has some potential. I think that there are some interesting things to look at here. And there's another article, this is with Hamid Reza Ibasi and myself, this is an archive, so I can also share it with you, where we eliminate noise. So we have, this is vortex shedding behind a cylinder. This is the reference at the top. We added a lot of noise, like really contaminated the signal. And PINS, what it's trying to do is to solve the runs equations from this data. So clearly, it's going to try to eliminate the noise that is inconsistent with the governance equations. No, so we can clean up quite nicely the data, even for very corrupted flow fields. Here, I'm showing you the temporal coefficient of one of the POD modes. Actually several, third, fifth, and seventh. So you can see, and this is for the case with PINS, no? So we can see that the third and fifth mode are in excellent agreement. We can really get rid of the noise and we get very good agreement. Even in the seventh mode, we can actually agree pretty well. So we are able to, well, quite effectively for this particular case, and this is of course a preliminary study, no? I mean, one can do something much more interesting with real data sets and with more challenging flow cases, but even in this simple wake of a 2D cylinder, we can actually try to remove some of the noise, no, and get some robust results there. So from PINS, there is quite some potential. At the end of the day, the advantage is that you don't need much data, because if you think about it, your loss function is the residual of the governance equation. You're just solving the governance equation. So the data that you need is basically to train the boundaries, no, the boundary conditions, but you don't need anything else. So in terms of data, PINS is not very demanding. And well, it can actually predict very well the mean flow, even the Reynolds stresses. So for some industrial applications and for some augmentation of experimental data, for some enhancement of some measurements, it can be an interesting approach. Okay, and I will not take much longer, so we have time for questions. But these are some of the some of the Christmas wishes, no, for future work. Being able to, and actually many of these things we have already done them, because this slide is a bit older, so we have behaved quite well. So we are now looking at coherent structures and tracking them in time with machine learning, so we can actually predict them quite well. We're using autoencoders. I will talk about this next week. This is very interesting. It's basically a nonlinear POD. So you can actually have a much more compact reduced order model than with POD exploiting nonlinearities. And there's some work in LES modeling, inflow and boundary condition generations, and basically being able to perform effective flow control and discover novel flow control strategies. So that's again for the seminar next week. And these are my conclusions. I showed you some of the potential for recurrent neural networks. We talked about PINS, and we also could assess a little bit the possibilities of PINS for both numerical and experimental data. This is my contact information, my email. This is my lab, the Vinuesa lab. My social media. I have also some videos in YouTube explaining some of this work, so you can actually have a look and look at some of the material that we have there. So feel free to contact me anytime. I'm happy to discuss and to collaborate and talk about interesting ideas. And for now, I'd like to thank you very much for your attention, and I will answer your questions. Thank you.
Thanks, Ricardo. That was an excellent talk and
thank you.
Beautiful introduction to AI applied to CFD. I'll open the floor for questions. But what I'll do now is, if there are any audiences online, I would give them the opportunity first to ask any questions. You can either unmute yourself, go ahead and ask the question, or type it in the chat and we'll read it out for you, and then we'll take questions from the audience here.
Hi, hello. Actually, I have 4 questions, if I may.
Just trying to talk, but we cannot.
Lorenzo.
Yes.
Maybe the audio.
We can't hear you.
All right, so I will write.
Yeah. Can you speak up now, Lorenzo?
Yes. Can you hear me?
No, still we can't hear you.
Sorry.
Okay.
This is in the maximum. Let's see in the audio. Select a speaker. So they are on the
Okay.
they are on this one, but I can put it on my laptop. Maybe we can hear it if I put the. Okay. Can you try again, Lorenzo?
Hello, now can you hear me?
We can hear you in my laptop, so the audience cannot hear you so well, but I can repeat the question after you say it.
Okay, I was writing, but okay. So I have 4 questions.
Okay.
And so the
I can
first
repeat all 4 of them.
all right, quite short. So first one is, what about the 35 negative targets, which you talk about in slide 8? What are they and why are negative?
The slide 8.
Oh, maybe.
Yeah. So which targets?
This 35%, why are they negative?
Why are they negative? That's a good question. Well, we went target by target, trying to assess whether AI would help or inhibit the achievement of that target. Generally, the positives are because AI allows a new technology or a new method that was not available before. Many of the negatives have to do, for example, with increasing inequalities. So if the future is going to rely on AI and now not everybody has the same type of access to AI, we're going to exacerbate the inequalities that already exist, and all the SDGs that have to do with inequalities, with zero hunger, with no poverty, are going to be negatively affected. So it's always things like that, unintended negative effects of AI.
Right, all right. And so second question is, in your opinion, which are so some application of unsupervised machine learning in turbulence field apart from POD?
Yeah, that's a good question. So the question is unsupervised applications of machine learning. There is a very nice work of Steve Branton's group, for example, where what they do is that they look at the covariant equations, Navier-Stokes equations or the Rans equations, and in the case of a boundary layer, they automatically cluster regions of the flow depending on the leading dynamics, on the most relevant dynamics, and they automatically detect the transitional region, the free stream, the inertial sublayer, the viscous sublayer, all these regions that we know from our physical understanding, because we know fluid mechanics, in an unsupervised way, they are located, they are identified. Of course, this is a problem that is easy, but if you start to think of applying this sort of approach to more complex problems where we don't know the covariant equations or we don't know the actual details of the physical mechanisms, I really see a lot of potential there on being able to basically do scientific discovery, being able to identify mechanisms that are hidden in an unsupervised way.
Thank you. Another question is in slide 37, when you show the pins architecture, there would be any problem to extend the pins to 3D and to time varying problems, so you run, for example?
That's a very good question. So this pin architecture is based on an MLP, on a multi-layered perceptron. So it's a very simple architecture. In 2D and steady is the most straightforward for this architecture. For 3D, it would be computationally much more complicated, but it could be done. I don't think that it would be very, very tricky to do it in 3D. Time is complicated. Time we are working, we have actually a couple of studies on being able to extend pins effectively to unsteady problems. And the biggest challenge there is that time becomes one additional spatial dimension. And remember that the MLP doesn't organize the data in space or in time. So suddenly all the steps are disorganized. The network doesn't know exactly how to do the temporal integration, and therefore it struggles with unsteady problems. We have tried combining this with an LSTM, for example. We have tried a time stepper to do the temporal treatment differently, and there is improvement of the results, but not yet fully satisfactorily. So that's something that is ongoing work. I think it's doable, of course, and that's a promising direction to go, but it's still something that we're working on.
Thank you. And finally, if I can, is there any like trend in the minimum amount of data which you can use in pins? For example, with respect to the simulations you presented, is there any specific trend? For example, the minimum amount would be like 10% of the full database, or it's dependent on the test case?
So when you talk about data, because for the data that we need is the data at the boundaries. And that's the only data that we need in this particular implementation of pins. Or are you thinking more about the number of collocation points?
The number of collocation points.
Okay, if you're talking about the collocation points, that's a very good question because, of course, the more points, the better. What you need to do is to propagate the information inside the domain to the boundary. Because our loss function has two terms. One term is the residual of the runs equations, and the other term is the deviation with respect to the boundary conditions. So you need to be able to propagate the information from the domain to the boundaries. If you have many points, you're going to propagate that better. You're going to be able to match the boundary conditions, but you will get a very expensive simulation because for the same mesh as runs, it's 10 times more expensive. So you want to minimize the number of points. If you have very few points, the problem is that you will not be able to propagate the information to the boundaries. So you will get something that doesn't need to be physically consistent with the boundary conditions. It will still give you something, but it doesn't need to be physically consistent. So there's a trade-off there. And here there is some heuristics in finding the optimal number of points. So you get something that is computationally cheaper than a traditional simulation, but at the same time sufficient to have a proper matching of the boundary conditions.
Thank you.
Yeah, thank you for the questions.
Thanks, Lorenzo. I'll move on to the audience here. If anyone sitting here would like to ask any questions, please, I suggest use the mic. Yep, Julio.
Thank you, Ricardo, for this very extensive talk.
Thank you.
In this particular case of the Reynolds average Navier-Stokes equation, when you're saying, when you go back to your neural network, you've got data. Is that data time dependent, or is it just?
It's a study. This is
just the statistical
the
data?
statistics. The statistics from the DNS.
Okay, so the statistics from the DNS is what's the input to the.
Correct.
Now, is that
at the boundaries? Only at the boundaries.
Only at the boundaries.
The rest
nowhere else. So
nowhere
else.
Giving
boundaries.
We just give boundaries.
So just from the boundary conditions. So why not use the data that you might have inside?
Yeah, if you have it, then it will be even better.
Yeah, because
so if you have data, and
that's why you need boundary conditions, because one approach about pins, as I understand, is that it can actually be used without the boundaries.
Yeah,
if you have data.
If you have data inside, yes. That was actually the original idea of using pins, that you have data that was not organized, so data that was all over the place, and then you would create an organized mesh with, yeah.
So, all right, that wasn't quite clear when you, that was just boundary condition data.
Yeah, so in this particular problem, we just use the boundary condition data, but you could use, if you have more data, then it's even better. Then it's even better. Of course, I mean, this particular example of using boundary data, the way that I think about it is you have, because of course, if you have the DNS, you don't need to solve inside. No, this is for experimental data. You have experimental data with limited resolution. That's your boundary data, and then you increase the resolution with the pins.
I mean, the data says it to solve the Navier-Stokes. So it's just another way of solving the PD.
It's another way of solving the PD, but
you don't have model. The model comes from your boundary conditions as well.
Exactly. I mean, because of course, if you want to solve the PD, well, you need a model for Reynolds stresses, and that's where the error comes. We don't have that problem.
Okay, but you actually need, your boundary conditions cannot be on the surface, because that would be zero.
That's okay.
I mean, if you go, let's say on the boundary layer, zero pressure gradient turbulent boundary layer.
So
if you go all the way to the free stream,
yeah,
all those Reynolds stresses are zero.
Yeah.
If you go to the wall, all those Reynolds stresses are zero. So you only have the inflow and the outflow.
Yeah. So that we tried, and it actually works. I mean, of course, the closer that your boundary data is to your domain of interest, the better. No, right. Let's go to the boundary layer.
So have you investigated how
close? So we investigated that. I mean, you can be in the far field, and this is of course zero, at the wall is zero, but then you really need the input and the inflow and the outflow. Yeah. You need those. And then, because one thing that we tried initially is, what if I have, my inflow is, the inflow is laminar, but we trip it, no? So the truant inflow that we know, and then the far field is 0, the wall is 0, and I can estimate the outflow. No, with boundary layer theory, I can see what the mean flow is going to be, and I can make some estimates for the Reynolds stresses at the outflow. If you do that, it will be very bad. So you need to have, if you're going to use the far field, the inflow and the outflow need to be good, need to be the correct ones. Because of course, what PINS is doing is basically to solve the governing equations. I mean, so that's the only thing that it's doing. Yeah, thank you for the question.
Thanks, Julio. Once, yeah, Caleb.
Sorry, just stimulated by that last question. Maybe I missed it. So, did you mention? Could you look at it in terms of putting? When you mentioned the laminar inflow, have you tried it with just say the laminar inflow, the turbulent outflow, and were you able to run it that way and maybe pick up where it transitioned?
No, that's a good point. We didn't do that. We didn't do that because, of course, these are the runs equations, and then you need to have to include some transition model, not to be able to. I mean, that would be very tricky. We didn't even try that because I'm not expecting to get anything reasonable there. But of course, if you now let's say that you have data inside the boundary layer somehow, huh? So in some plane inside the boundary layer, and then your inflow is laminar. Then maybe with that information, you can inform the network to get something of the transition location. We didn't try that, and this is me just guessing, no, but could be something to look at. Or alternatively, to try to add some term to the runs equations to try to model the transition, but then you're modeling, no, and we're trying to get away from modeling. So yeah.
Nice.
Yeah, thank you.
Thanks, Caleb. Tronio.
Thanks, Ricardo, for the great presentation.
Thank you.
I was wondering about the LSTM method, and you applied it for the Wheeler flow, right?
Can you repeat?
You applied the first method, the LSTM, to the Wheeler flow, right? With only 9 models in Molly's paper. I was wondering about the performance of this model for the fully turbulent one, because that's just like a kind of synthetic.
Yeah.
Kind of
so I can share. I didn't show it today because it was only introduction, but I can share the paper with you. We have it. We published it last year. We did it on a minimal channel. So on a minimal channel, I mean, the main difference between real turbulence, even if it's just a minimal channel, which of course has simplified temporal dynamics, but still it has all the ingredients of turbulence. The difference between turbulence and the 9 equation model is that the 9 equation model has only one scale. So everything happens in the near wall. But with turbulence, you have several scales. You have separation, even if it's a very low Reynolds number and it's minimal, you have some range of scales. So when you're trying to predict the temporal coefficients of the, let's say, 100 POD modes that we get from the minimal channel, you start to classify modes of different frequencies. So we got low frequency, middle, and high frequency modes, and we have to train different models to be able to capture all the temporal dynamics that we have there. That's the biggest challenge of going to turbulence, that not the same neural network is going to be able to tackle all the temporal frequencies of all the modes. By the way, that's something that is solved with a transformer. That's as a side note. The paper that we published last year was with LSTM, but with the transformer, you solve the problem of the multi-scale character of turbulence. So that's also something to add to the mix. Yeah.
Thank you.
Yeah, thank you for the question.
Thanks, Petronio. Anyone else? Well, if not, please join me in thanking Ricardo for an excellent talk. Thank you, everyone, and we'll see you next week.